Hi everyone, we're going to talk about the practice problems for exam 3. Alright, so kind of talked about this chart in general. If you have it memorized, it will help you quite a bit, but essentially it tells you if the alkyl halide is primary, secondary, tertiary, or methyl, what's going to happen. If it's secondary or primary and you have strong nucleophile, you automatically know it's going to be SN2. And the only time it's really, you're not sure is this one right here. So if it's secondary and you have a strong nuke and a strong base, you're usually going to have both SN2 and E2. And then also if it's secondary and you have a weak and a weak, it's going to be SN1E1, SN1E1. So understand this chart really, really well. Have it down. I'm going to go over a few examples of strong nuke, weak base. So let's see. So strong nuke, weak base examples, they say I minus, Br minus, so any X minus, actually really I minus, Br minus, because Cl minus it becomes not as good of a strong nuke. So the bigger ones, the further you go down the periodic table. We also talked about stuff that's like an S minus or an SH minus. Okay, so, or not even SH minus, sorry, something bound to an SH, so some R here and some R here. And we also talked about things with SE. Somebody asked in class about selenium. So things with selenium on them are also tend to be strong nukes, but weaker bases. Strong nuke, strong base, that's usually some R to an oxygen that's negatively charged. That's the most common case. Yeah, that's about the most common case. And then we have strong, bulky bases. This is usually when we have a strong base, but a weak nuke. All right, so the strong base, weak nuke aspects are usually when you have a strong, bulky base, which is going to be something like this, the tert butoxide, the darn bulky unit, DBU, or DBN. Okay. And then we have a weak nuke, weak base. That's usually an R to an O, but with an H on it, okay? So any kind of alcohol is going to fit into that category. One other thing that you might encounter would be like a CN minus, and CN minus is kind of more like a strong nuke. It's a moderate base, but we'll count it as a strong nuke, strong base, so you don't have to learn moderate stuff as well. Okay, let's get started. We're going to go through all these examples just real quick. We're not going to do the mechanisms. That's mainly because I have 30 minutes to film this video, so we're just going to do what we can. To remind you, if you have something from the first column of the periodic table that's got a 1+ charge, so sodium, for example, is right here on the periodic table, so you just get rid of it and replace it with a negative charge. So really this is just saying an SH minus. So if you have an SH minus, you go over here, SH minus, that's a strong nuke and a weak base. Okay, so it's going to be a strong nucleophile. If you have a strong nucleophile, it's going to react, so this is a strong, usually via a substitution reaction. But the most important thing you want to pay attention to the fact is this is secondary. To remind you of how you tell if something's secondary, you look to the carbon that the alkyl halide is attached to, and then you see how many carbons that's attached to. In this case, there's 2, therefore it's secondary. So you're like, okay, secondary, you've got something with SH, that's a strong nuke, weak base. Okay, so it's going to be a reaction via SN2. All right, SN2 reactions, we know result in the opposite of whatever you had, because that nucleophile has to attack from the other side that the alkyl halide is on. And then the alkyl halide can leave. I told you I wasn't going to do mechanisms, but this one's just so easy, I'm going to do it. So when this attaches, it has to attach, therefore, on a wedge. All right, let's keep moving. Here, this is also strong. And this one right here, the chlorine is attached to that carbon is attached to just one carbon. This is primary. Okay, so we have a primary. This is strong nuke and base. Anytime you have that O negative charge, if it's not a bulky base, it's going to be a strong nuke and base. Okay. But you go over here, you're like, okay, this thing is primary, it's attached, it's got a strong nuke and a base right here, it's going to be SN2. Now, depending on which class you're in, one of my classes we discussed the fact that E2 would be a potential product. It's just not going to be as much of a product, okay? So this will be your final answer. And again, if this had been on a wedge, that would have resulted on a dash, etc. Okay, on to this next one. Cn minus, we just said that this is a strong nuke and a moderate base. So, strong nuke. And we said we'll treat it as a strong base. The next thing we want to know is, what is this? Well, this is secondary. Look at that. It's got 2 carbons. So this, therefore, is a secondary carbon, or alcohol halide. So you go to secondary, strong nuke, strong base, SN2, and E2. So the SN2 is pretty straightforward. We've been doing them already. Okay, we know if this is a methyl group, we're not touching that methyl group. And we know if this one was on a wedge, that the resulting CN, whoops, I just messed up, must be on a dash. This is a dash, in case you can't tell. The other thing we should be paying attention to is the E reaction. Now, for an E2 reaction, we know that this is going to grab a hydrogen. If this is our alpha in the purple, our reds are our betas. And you're always going to draw the double bond between the alpha and the beta. Okay, so the double bond will either be here or it'll be here. You want to look to see if one of those things has more carbons than the other. They both aren't, they both don't. They both have the same number of carbons. This one has 2, this one has 2. And so it doesn't matter which one, you'll get them in equal amounts. So again, this methyl group on both of them won't be touched, but you'll have a double bond here between that alpha and that beta, and you'll have a very similar one where the double bond is here between that alpha and that beta. All right, now we have, I noticed right away this is weak, and I know that weak nukes and weak nukes, especially if it's going to be a substitution, prefer tertiary, and I see that this is tertiary. Okay, again, it's weak because we know it's some R to an OH. Okay, so this is tertiary, and therefore the resulting product will be, I'll show you, use this. The resulting product for something that's tertiary, when you have weak nuke and weak base, will be an SN1 and E1. And SN1 and E1 usually go together, so you'll get really used to that. For the SN1, don't forget that the product has to be a racemic mixture, because this thing leaves, the bromine leaves first and foremost in an SN1 reaction and an E1 as well. It leaves, and if it leaves, then there's no stereochemistry here. So this nucleophile can come in either direction and attack, and because of that, you'll have a racemic mixture. I'm going to have to draw it really small because there's a lot of products here. Okay, so you'll have one where the O, CH2, CH3 is there on a dash. You'll have one where it's on a wedge. Let's do the dash there and the wedge there. Okay. So these are our 2 SN1 products. Then you have your E1 products. Yay! Okay, there's some crazy business with our E1 products. The crazy business is this. If this is our alpha, and we draw the 2 betas here and here, there's hydrogens on either of them. Neither is more substituted, so both will result in, both will give you a product. Okay. The problem is, as soon as this bromine goes away, these things are free to spin around. Okay. And they're actually, well, they're still free to spin around now. But when the bromine goes away, this thing might spin up, it might spin down. You don't really know. So you'll get a product. You'll get 2 for each double bond. Let me show you what that's going to look like. Okay. So for the first one, let's make it simple. You'll have boom, 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 boom. Okay. You've got a methyl group there. And you're going to have that there. Okay. But again, these things can flip around. So one of the easier things to do is just find which side is the smallest. And what I mean by flip around is you're looking on either side of this double bond. And hopefully you agree in this, if you turn it kind of this way, you've got 2 methyl groups pointed up and this big long butane group pointed down. So what I'm going to do is I'm going to turn one of those methyl groups around, and that will give us the appropriate product. So I'm going to start with the exact same thing, like that, but instead of the methyl group pointed up here, I'll draw the methyl group pointed down. So these are both our E2 or E1 reactions. And we'll also have between this alpha and that beta, and we'll have the same thing. Sorry, I forgot to throw the methyl group on that one. Okay. And we'll also have this. Okay, where we have the methyl group there, and now the double bond there. And then I'm going to draw that exact same thing, but I'm going to put this methyl group, or this ethyl group right here, and the methyl group, I'm going to switch them around. Okay, so what I mean by that is let's just start with the double bond. And on this double bond, initially we had a methyl group pointed up and an ethyl group going down. So I'm going to draw the methyl group going down and the ethyl group going up. Okay. And that would be all the potential products for this reaction. So when you have a weak nuke and a weak base on a tertiary, get excited because there's lots to do. All right, when it comes to synthesizing reactions or attempting to figure out what something reacted with, you know that this is an alkyl halide, so it would be leaving, and it looks like it attached to an O to this cyclohexane. So pretty much all you're going to react it with is that O with the cyclohexane. Now the question is, do you add an H to that O or not? You don't, because this one is primary. There and there, the alkyl halide is primary. What does that mean? Well, if it's primary, that means it wants to occur via an SN2 reaction. We know primary SN2 reactions prefer a strong nuke. So you can do a strong nuke and a weak base, but that doesn't work. So we have to do this thing right here. So it would react with O negative, and hopefully that makes sense. You wouldn't put an H on there because you know that that would be weak and it wouldn't react with a primary. Okay, moving on. Now we have this is a weak nuke and base. How did I know that? Because it's HOH, so it's an H, or it's got an OH group on it, essentially. And we know that this is tertiary. So if we have a weak nuke, weak base, weak nuke, weak base, tertiary, SN1, and E1 is going to be what will react. So we know that with SN1 and E1 reactions, it always wants to choose the more substituted. But in this case, if that's our alpha and these two are our betas, neither one of these betas is more substituted. So we'll get the double bond here and we'll get the double bond there and not much else. So we'll get this. You still have a methyl group. We'll get the double bond here and methyl group, double bond there. So that's our E1 reaction. Then we also have an SN1 reaction. With an SN1 reaction for all these weak things, you essentially just kind of take off a hydrogen because that's the last step that happens if you follow through the whole process. You know that a hydrogen just eventually comes off. And so you're taking this OH and substituting it with the Br. But you also know that this is an SN1, so that gives you a racemic mixture. So if you have something originally on a dash, it's going to end up on a wedge and a dash. Okay, so we'll keep the methyl group there and we'll put our OH there. And we'll do the same thing, but we'll switch the wedges and the dashes. Again, we're not touching this one because it was never even affected. Okay, and those are your products. Moving on through these, here I have a primary. So I'm automatically thinking probably SN2. And this is strong. This is strong nuke and base. So I go to primary, strong nuke, strong base, primary. It's going to be an SN2 reaction. So I know that it's going to go whoop, 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 and then O, CH2, CH3. Okay, now we're on to this fun one. So anytime you see two equivalents of this is a strong base, by the way. Strong base, weak nuke. I didn't provide you those examples, so let's go over here. So for a strong base, weak nuke. That's because I just said strong, bulky base. But strong base, weak nuke, an example would be any kind of H minus, okay, or NH2 minus. Those are pretty much the most common forms that you'll see. So H minus or an NH2 minus. So you have an NH2 minus. Sometimes it says two equivalents in your book. Sometimes they just don't and assume that you know that there's excess there. But the main thing is, do you see two alkyl halides? If your answer is yes, that means triple bond. Essentially what happens is an E2 reaction twice. Okay? And so it's slightly more complicated than that, which is why they don't even go over the mechanism in your book. But I already screwed it up. I'll show you why I screwed it up. Because, but you probably want to do the same thing. I like drawing the whole thing out, and I know that this is going to form a triple bond. The question is, where is the triple bond going to be? Is it going to be there? Because if it's there, then I have 5 bonds on this carbon, and I can't have that, right? So it's going to be here. Okay, it has to be there. Now we know that a triple bond would be an sp hybridized, which makes it linear. So really, I shouldn't have drawn it like that. I should have drawn it like this. Boom. 1, 2, 3, boom, boom. Okay, and that would be the appropriate answer to this. Okay, here we have, this is attached to one carbon, that carbon is attached to this. Okay, so we have a primary. Now primary things normally they much prefer a substitution reaction, right? But this is a darn bulky unit. So with that darn bulky unit, if you have primary, you can force it to go E2. So we're going to force it to go E2, and we know that that double bond has to form between the alpha and the beta. You only have one choice for alpha beta, so this should be kind of a fun one. You should be like boom, boom, done. Here we have a weak nuke and base, and this is tertiary. So in those situations, we cry, okay? So just do one thing at a time. Let's focus on the substitution reaction first. The good news is there's no stereochemistry, so we don't have to draw a racemic mixture. That goes down there. And we know that this would be an OCH2, CH3, that H eventually goes away. Okay, so this would be our SN1. And then we'd also have an E1 reaction. Our E1 has a couple of options. If this is our alpha, we actually have 3 betas, boom, 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 okay? Hopefully you agree these two are more substituted. So you'd have equal portions, this and this, but these are actually, and I don't think I even did that in class, these are actually equivalent because they're all attached to the same thing, okay? So you can choose either one of them, they're equivalent. What I mean by that is if I flip this thing around, these two can spin. If I flipped it around, you'd get the exact same thing. The stereochemistry here and here is not specified. All right, so I would get, let me draw it over here, boom, 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 and then I'd have that, and then I could draw, again, the double bond here or here, doesn't matter. Let's put it there, plus, boom, 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 boom. Okay, so you'd also have it there. This would be our major because it's more substituted, and this one would be our minor. All right, on this next one, ooh, I see 2, boom, boom. This, we know that N plus goes away, replace it with a negative, so it's NH2 minus. That's a really strong base. It's just like this thing right here that we did earlier. And so I should be super excited. I know this is going to be forming a triple bond. The question is, where is the triple bond going? It can't go here. It has to go between where those two things are. So we get doosh, 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 like that. Sound effects and everything. Okay, on to this one. Here again we have weak. Got a phone call. Turn it off. Okay, so here again we have weak. We have an alcoholite. It's attached to 3 things. 1, 2, 3. So this is tertiary and weak. That's again where we cry a little bit. The first product we'll get is this. If I flip that around, I'd get the same thing. Okay, so that's our E1 product. This is going to be our major E1. We would also have a minor E1, which would go there, okay, between this alpha and that beta. And last but not least, we'd have our SN1 product, which would be this. We still have this methyl group, and then we'd have an OH attached to it. Because there's no stereochemistry, this is a symmetrical, like meso compound, right? Well, it's not even meso. These are the exact same things here and here, okay? So it's not a chiral center. So you don't have to worry about stereochemistry. All right, then we get here. We know that we started with something, and we added SH minus to it. SH minus is a strong nuke. It tends to be a weaker base. Okay, so if it's a strong nuke, we know that it attacked this thing, but this has stereochemistry on it, which means our initial thing had to have stereochemistry on it. So hopefully you agree at the very least we had something like this to start with. The next question is, what was here? Well, if this was a strong nuke and this thing was secondary, that means it had to react via an SN2 reaction. We know an SN2 reaction always gives you the opposite answer. So if this is a wedge, that means our initial X had to start on a dash. Someone in class asked if you can start with an X, you absolutely can. I'm just gonna throw a bromine on there just because bromine's one of the more common ones to use. So this would be our answer. If we reacted this with SH, we would get that as our product. Okay, moving on to some synthesis. It asks you to make these essentially. So the first thing we do, we'd start with something. Let's say we started with a bromine, and you want to make this. Well, in order to make that, if this is primary, you want it to react via an SN2 reaction because primary things prefer SN2. If it's SN2, that means you're probably going to react it with a strong nuke, or a strong base would be the easiest thing to do, or a strong nuke weak base like this SH minus, and that's in fact what we did. So you take an SH minus, and boom, shakalaka, you would get that as your product. Now over here, it's a little funkier, but anytime you see an ether, a resulting ether, that means one part was a nucleophile and one part was the electrophile. So you can start, let's say we started with this section right here, 1, 2, 3, 1, 2, 3. And then we reacted it with the other portion right here. So it'd be like an O, doom, 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 and it would have to have a negative charge. This is the fun part because you can just make up whatever you want to react. But this, you would get this product because this would come in, that would come off, and you'd get that as your final answer. So hopefully that helps. Okay. Draw the major stereoisomer formed when each compound undergoes an elimination reaction with OH minus. OH minus is a strong base. So it's saying, hey, don't worry about the nucleophile part, just tell me about an elimination reaction. So both of these might have an SN2 product. But you know that you cannot form a double bond here, if this is our alpha, by the way, and these are our betas. You cannot form a double bond between here and here because then that would have too many things on it, okay? So it has to go between here and here. Okay, here's the difference between these things, though. What makes it really important that we pay attention to this fact. We know that it's always grabbing a hydrogen off of this. And up until now, we've had 2 hydrogens on almost every carbon we've grabbed. Here, we only have 1 hydrogen, and it has to be on a wedge, right? Like that. Okay. If this is on a wedge and that's on a wedge, that's not good. Both on wedge? Nope. It cannot happen. So if, for example, you're stuck in a cyclohexane ring or a ring, nothing can spin, you're stuck. Here, though, this thing can actually spin around this bond right here. Okay. So it gets a little funky, but we're going to have to, it's going to pull off the hydrogen here. The OH minus is going to grab the hydrogen there, and that's going to fall and make this chlorine fall off, but only if and only if this part spins first, or one of the parts spin first. Okay, so one of the better things to do that I like to do is just draw. I'm drawing from the double bond right here. Draw what you see. Okay, so hopefully you see that I started here, that put a double bond between the alpha and the beta. I drew what I saw. I know there's a methyl group right there. Okay? And then you look at the other part on the other side, this stuff right here. And where it was pointed up, you know it now has to point down. So that's where I'm going to draw doom, 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 like that. Okay? And that would be the only product that occurs with this reaction. If you happen to have drawn this up, that would not be the correct answer because it was impossible. These are syn-periplanar. They're in the same exact plane. Now we go over here, and here we have the hydrogen there. We have the exact same thing almost, except now our chlorine's on a wedge and our hydrogen's on a dash. And that can happen, so we don't have to switch around anything. In fact, we should keep it all exactly the same. We would draw it exactly the same. So I'm going to draw that double bond with the methyl group, and then I'm going to draw this up like that. Okay, so everything's drawn exactly the same here. But here, remember, we had to flip that down, otherwise it would not have occurred. Okay, moving on to the protons. It says, how many different protons groups are in the following? This one has one there. There's a hydrogen right here. In fact, I'll draw it in purple. And these all have 3 hydrogens on them. But hopefully you agree they're all a methyl group attached to the same thing. There's a lot of symmetry here. So these would all count as 1. Okay. So we got 3 methyl groups that are exactly the same, and we have that. So this only has 2 different proton groups. Looking to this one, there's a lot. I'm going to run out of colored pencils. But because there's not really any symmetry in this molecule, if you flipped it around, it's not the same. Even though this is a CH2 and this is CH2, they're attached to 2 totally different things. This CH2 is attached to a CH2 and a methyl. This CH2 is attached to a CH2 and an oxygen. Totally different groups. So we got 1, 2, 3, 4, 5, 6, 7 different groups of hydrogen atoms there. And last but not least, we have this one, same thing. There's really not much symmetry, except I can see these 2 are both methyl groups coming off of a carbon, so these are equivalent. Okay. So this and this would be equivalent. So that's 1 group. Here's 2 groups. Here's 3 groups. This doesn't have anything on it, okay? And here would be 4 and 5. Okay, I wish I had a different color for that. So pretend different color. So I count 5. 1, 2, 3, 4, and these 2 are the same at 5. Okay, we are on to this part now. It says, propose a structure consistent with this. If you were to look at the peak information that you'll be given on your exam, you would see that this means that there's sp3 hybridized hydrogens, telling you that this is all alkane. If you wanted to prove it to yourself that it's all alkane, you could use the following. You could say, let me pull this out real quick. You say, I know this is all alkane because I know that 2 times the number of carbons minus, or plus 2, minus the number of hydrogens, let's see, plus the number of nitrogens, minus x, all divided by 2, sorry, I usually do plus n minus x, is going to give you the degrees of unsaturation. Okay, so a degree of unsaturation, remember, is equal to like a double bond or a ring. Okay, so if we take 2 times the number of carbons plus 2, that's 10, minus the number of hydrogens, which is 8, plus 0 for the number of n, minus 2 for the number of x, and we take all of this and we divide it by 2, we get an answer of 0. This would be 10 minus 8 minus 2 would be 0. Cool. So there are 0 degrees of unsaturation in this thing, meaning it's all alkane. Okay. So why is that important? Well, we have 4 carbons, and we've got 2 bromines. We don't know what they look like. I'm just drawing some guesses. You could have both bromines here. Okay, you could have, there are very, very, very many options, but the important thing is there's no rings and no double bonds. You knew that again because this told you it was all sp3, and the formula of unsaturation told you that it was all alkane. Okay, so let's go ahead and try to figure this one out. It's saying you have a singlet at 1.87. Remember, the numbers go up this way. So at 1.87, you've got a singlet, and it's 6H. Its integral is 6. I mean, there's 6 hydrogens that see no neighbors. Go over it. Here we have a singlet at 2H, with 2H at 3.86. This one, because it's farther downfield, is closer to the bromine. So let's start with the one that's closer to the bromine. I've got a carbon and it has 2 hydrogens on it. That's what this means. There's a carbon with 2 hydrogens on it. And when these hydrogens are jumping up and down, they look and they see no neighbors. They see no neighbors. And we also know that it's close to the bromine, meaning one of those things is probably a bromine, and the other one must be some kind of carbon that has no neighbors on it. If this carbon has no neighbors on it, then remember there's only 4 carbons. One of them must be attached to something. One of them must be attached to something else. None of those can be hydrogen. And one of them must be attached to something else. But there's only 4 carbons. So this one must be attached to a carbon, this one must be attached to a carbon, and this one must be the other bromine. Okay. Now let's look at this other one. This 6H is telling us that there's 6 hydrogens. Anytime you see 6 hydrogens, you usually should think 2 methyl groups. So the only place that goes in is right here where we have 2 methyl groups that are just waiting to be filled in. Okay, because if these are the methyl groups, if you look and say they're jumping up and down on the thing, if they look to their neighbor, their only neighbor here, there are no hydrogens on it. The reason I know there's no hydrogens, again, is this is single. And we know that this follows the n, the number of neighbors, plus 1 rule. This means there are 0 plus 1 in order to get 1 single peak. So this is the only possibility. If you wanted to draw it prettier, you could draw it something like that. You put the bromine anywhere you want to. All right, I'm going to run out of time. So, okay, on this next one, I'm sorry if things got shifted a little bit. I had somebody come by the office and I had to run and teach a class. So we are starting over again with this one. I don't remember where I was at, but it says there's 3.5. There's a triplet. A triplet means 2 neighbors. Again, that's because the n plus 1 rule. So if it gives you 3 signals, that means it had 2 neighbors. And here at 2.4, there's going to be a quintet. That means 1, 2, 3, 4, 5. What that means is 4 neighbors. So 2 neighbors and 4 neighbors, because 4 plus 1 equals 5. Okay, but it doesn't tell you the hydrogen numbers, right? It doesn't say, hey, if we're focused on this one, how many hydrogens are on it? But there aren't too many possibilities with C3H6, so it really wasn't necessary. Let's talk about a few possibilities before we go into solving this. For example, you could have a bromine here and a bromine here. Okay. You could have a bromine here and a bromine here. You could have a bromine here, let's say, and a bromine here, and then you could have something like this. Okay, there's several possibilities, but there's not that many. In fact, we're almost already out of options, because if you flip this around, you get that round. You could also have a bromine and a bromine. But outside of that, there really aren't that many things. Okay, and this tells us that there's two different kinds of signals, meaning there was probably some symmetry in this thing because there aren't three individual peaks. So for example, this one would have given us 1, 2, 3 different signals because there's 3 distinct groups of hydrogens. This one, however, for example, would have only given us, this and this are identical, so this one would have only given us 2 signals. And this again, this one right here would have been similar. It would have only given you 1 signal because there's no hydrogens here. All right, and this would have given you 3 distinct signals. So this one would have given 3, 3, 2, 1. Nevertheless, let's pretend we don't even know this. Let's see if we can figure it out. There must be some symmetry though if there's only 2 signals. The first one is at 3.5. That's the one that's going to be a carbon. And let me color coordinate this. So the carbon will make it blue. That carbon is attached to another carbon that has 2 hydrogens on it. Okay. And this one, and also this carbon, is probably attached to a bromine. Okay. The reason that's important is because the reason I know that is because this is the most downfilled one. So if it's at 3.5, it's most likely the one that's attached to a bromine. But the other one's also relatively high at 2.4, telling you it could also be attached to a bromine. So let's see if we can think it through. This signal has 4 neighbors, okay? So most likely a CH2 and a CH2. Okay. We, again, don't know how many hydrogens there are on this sucker. So this could actually be from 2 different carbons giving us this signal. And in fact, that's what I think it ends up being, because if this has 4 neighbors on it, then that's a CH2 and a CH2. So let's say now this one, because it's the only other peak, right? It has to be this carbon now that we're talking about. And that carbon has a CH2. And the other one has to be a CH2, right? And then if I do this, then that means the only other place I can put the bromine is right there. And that would make sense as to why you had just 1 signal for the blue and 1 signal for the red. Okay, let's double check it and make sure. This red carbon, right? Even though it didn't say 2H, we could make it a 2H. We write 2H. And it had carbons with 2 hydrogens identical. Okay. And that would give you 4 neighbors. 2 plus 2 is 4. And then you add 1, that's how you got the quintet. And then you look at the blue. Each of these things only had 2 neighbors. 2 plus 1 is 3, and that's why you got the triplet there. Yep, that makes sense to me. It's this one, which we could have already just figured out looking at the number of signals and drawing them out, but that was a fun one. I like it. You can see that these are always puzzles, and this would have been a 4H because you have 1, 2, 3, 4. In case you don't see, this and this are identical. That, and then this red one right there. All right, I hope that helped. Have a good one.